Hey guys! Today is our last day of Unit 10, and most of Unit 10 has been focused specifically on gases. And so typically what we do at the end of the unit is we kind of go back and look at all three states of matter, kind of an overview of those and how you think about kind of the phase changes between solids, liquids, and gases. And so I've got kind of a little table for you just to summarize, what we learned early on in our first unit on matter. And so when you talk about the states of matter, there are solids, liquids, and gases. And so the way the table is arranged is the first bullet is kind of talking about it from the tiny submicroscopic view, and the second bullet is more of how it behaves on the macroscopic big level. And so the first bullet for solids, the particles are closely packed together with the atoms vibrating in place. And so that kind of looks like the particle drawing there. Everything is nice and orderly, all kind of stacked together. The atoms vibrate in place. And as a result, solids tend to take on a set shape and volume. Because their atoms are just vibrating in place and not really moving around, their kinetic energy or energy of motion is going to be low. Now, for solids and liquids, what they share in common is that their particles are still close to each other, but what's different about a liquid is they now have enough energy to slide past each other as well. And so as a result, liquids, they have a set amount of volume, but they can take on the shape of whichever container we put them in. And then finally, gases, which we know have particles that are far apart. They're moving at very high speeds, so they'll have a high kinetic energy. And as a result, gases can take on any shape and any volume, which is what makes them good at expanding. And so when we talk about phase changes, it's just a change that occurs between any of these two states of matter. And so you're probably familiar with several of these already. So going from a solid to a liquid, that's called melting. A liquid to a gas is vaporization, or you may hear this sometimes referred to as boiling. That's the same thing. All right, but note, vaporization is not the same thing as evaporation. Vaporization and boiling occur at a specific temperature, the boiling point, while evaporation doesn't have to be at that same temperature to occur. So then if we follow that in reverse, if we go from a gas to a liquid, that's condensation. So for example, if you take a cold water bottle out of the fridge and you're drinking it on a hot summer day, the hot air, the gas that's in the air, is going to condense on the outside of your water bottle, and that's what forms the little droplets that sometimes people will say, oh, my water bottle is sweating. So that's the condensation of the hot gas molecules in the air to liquid droplets on your water bottle. Then we have liquid to solid, which is called freezing. Now the two on the outsides are a little more probably unknown to you. And so when you're going from a solid to a gas, that's called sublimation. That's a direct change where you just skip the liquid phase altogether and go directly to a gas. And so the way I remember that you're starting at a solid is because it's solid sublimation. So from a solid to a gas is sublimation. And typically around this time in the year, we do a dry ice lab. And so if you've ever seen a block of dry ice, how it kind of looks like it's steaming or giving off gas, what it's doing is it's sublimating or subliming, where that solid dry ice is going directly to a gas. Now, if we were to reverse that and take the gas back to a solid, that's going to be called deposition. So the gas is going to deposit itself as a solid, all right? Now, as we're going from a solid to a gas, we're having to put in more energy. Energy is being gained. So from a solid to a gas, energy is gained. Then, if you're going back from a gas to a solid, energy is being lost or released, rather, along the way. So what we tend to do kind of next in our lecture is I ask you a question kind of based on an experiment. So, okay, let's say that we wanted to observe, the phase change all the way from a solid piece of ice to steam, which is just water in the gas phase. And so let's say we went into the lab and I gave you a cup of ice, all right, and a thermometer, and I asked you to put it on the hot plate and turn the hot plate on, okay? Then what you're going to be doing is measuring the temperature or the change in temperature that occurred as you continued to melt the ice. And so what you would expect to see is the ice would start out solid, then it would melt to liquid water, then it would start boiling to form gas. And now keep in mind, you have the hot plate on the entire time. And so let's predict right quick, what do we think is going to happen to the temperature that we measure throughout these phase changes? And so most of the time when we ask this question in class, our prediction is that as time passes, as we keep melting from solid to liquid, then vaporizing to gas, we should expect the temperature to go just straight up. And that's because we've got the hot plate on the entire time we're supplying energy. But then kind of what we do is we've made our prediction and then we look at the actual results from this experiment. And so what's very interesting is that our prediction does not match the actual results. And so here's a picture of the actual results. And instead of being one straight line up, it almost looks like a stair step. So as we apply heat over time, at first the temperature raises, then it stays constant, it raises, then it stays constant, then it raises one more time. So then we normally spend some time kind of answering some questions and trying to figure out what's happening. But we'll go ahead, since we're doing the video, and just kind of jump straight to what you need to know. So first of all, the kind of three vertical regions on the graph, A, C, and E, those represent the three states of matter. So you have solids at lower temperatures, liquids at medium temperatures, and then gases at high temperatures. The flat portions of the graph represent the actual phase change. And if you notice, they're paired with a certain temperature. So the phase change from solid to liquid, that's called melting. And for water, that occurs at 0 degrees Celsius. The phase change for liquid to gas is vaporizing, and for water, that occurs at 100 degrees Celsius. And so what we see is that the temperature stays constant during the phase change, but the temperature rises in between phase changes. And so let's go back to our notes and see if we can write down some things that we've learned. All right, so on to the second page. And so here it's already labeled for you, solid, liquid, and gas. But what I do want to pencil in is kind of the freezing point, and that's just the temperature at which something freezes. For water, that's 0 degrees Celsius. And then I also want to pencil in the boiling point, which would be the temperature at which it boils or vaporizes. So this would be the boiling point. And again, for water, that's 100 degrees Celsius. So right quick to the side, let's write ourselves that reminder of the fact that during a phase change, the temperature is constant. And right quick, I'm going to try to give you a short kind of explanation of why. So as we're going kind of from a solid to a liquid to the gas, you'll notice that gradually the particles are kind of being spread further and further apart. And so what happens is during the phase change, all of the energy from the hot plate is having to be used to separate the molecules to generate the next phase. So since all of that energy is going into kind of separating the molecules, overcoming their forces of attraction, there's no energy that's left to be used to raise the temperature of the molecules. Temperature is just a measurement of the kinetic energy of the molecules, which is how fast they're moving. Now, in between the phase changes, since they're not focused on pulling the molecules apart, that extra heat energy can go into making the molecules move faster. Since they're moving faster, they have a higher kinetic energy, and therefore their temperature is going to raise. So here's how we're going to summarize that right quick. So during a phase change, the temperature is constant. And let's just add in the word because. Because the energy is used to overcome forces of attraction between the molecules. Forces of attraction between the molecules, and those are known as intermolecular forces. You might remember those from Unit 6. Okay. And then, so the second part to this that we're going to write down is in between phase changes, the energy is used to increase the speed of the molecules. To increase the speed of the molecules, which that's just the kinetic energy. So the temperature goes up or increases. All right. And so you've kind of got our graph already labeled, so we're going to skip this little table. But just know as we go from left to right, we're adding heat energy. As we go from right to left, we're decreasing the heat energy. All right. So now the last part of this lesson is we've talked about kind of a phase change diagram. And now we're going to transition to the last part, which is called just a phase diagram. Now what this phase diagram does is it tells you a certain temperature and pressure at which you can have different states of matter. And so it kind of looks like a Y almost that divides this graph into three different portions. So the solid portion is on the left, and that's because solids tend to be found when the temperature is low and the pressure is high. High pressure kind of keeps everything compact, and low temperature keeps them from moving around a lot. Gases are kind of the opposite. They tend to be found at high temperatures and low pressures. Gases don't like to be squeezed together, but they do like to move around very quickly, which corresponds with the high temperature. Then finally, we have the liquid area right in the middle. And that kind of corresponds to medium temperatures and medium pressures. Now, a very special point kind of on the graph that we're also going to take the time to note is what's called the triple point. And so we're going to add in this note is that at the triple point, all three states of matter coexist in equilibrium. And so what that means is that at that temperature and pressure, the solid, liquid, and gas state of the molecule are present all at the same time. And so in our dry ice lab, typically in this unit, you actually get to see the triple point of dry ice, where we have the temperature and pressure adjusted so that you can see it as a solid, liquid, and a gas at the same time. It's super, super, super neat. All right. Then last thing, with the phase diagram, if you adjust, the temperature or the pressure, you can transition between phases. Again, if you're passing from a solid to a liquid, that would be melting, while passing from a liquid to a solid would be freezing. And these boundary lines that you see, they kind of note the temperature and pressure at which that phase change can occur. Okay. So right quick, let's try this practice problem over here on the side with our phase change diagram. So it's basically just graph reading skills. It says, in what phase is carbon dioxide at 72 atmospheres and 0 degrees Celsius? So let's go ahead and find that kind of point on our graph. So 72 atmospheres will probably be close to the top of our pressures. 0 degrees Celsius will be somewhere kind of between -56 and 31 and +31. So maybe kind of in there a little bit, or maybe a little bit further over, maybe like that. And so if we kind of create in that ordered pair, it looks like the phase of carbon dioxide at that temperature and pressure is going to be a liquid phase. Okay. So now we've got a second question. It says if we start at this point above, so that point that we just marked, what phase change would eventually result from decreasing the pressure? So if we decrease the pressure, we'd be making it go down. And so what will happen is a liquid will be turned into a gas. So we have to think, okay, what do we call that phase change from a liquid to a gas? So I'll give you a second to think about that. All right, very nice. So a liquid to a gas is vaporization. Okay, and so right quick, I'm going to do just a few more phase diagram practice problems with you from Plickers right quick. So let's see, let's do this one. So it says a phase change from C to A is known as what? So if you remember, C is our solid phase, A is our gas phase, and so we would be passing from C to A. And so solid to gas would be sublimation. All right, so C to A is sublimation. Now, I'm going to give this a little bit of a harder one right quick. Let's pull one of these guys up. Okay, so, all right. So let's try this one. I know I've got the answered mark, but I'll kind of show you how to work through this one. So the idea is that they're wanting us to find a result at 30 atmospheres of pressure, which will be right here on our y-axis. And it's asking us to find the boiling point. So the boiling point will be the temperature at which we're transitioning from a liquid to a gas. So here's our liquid in B, here's our gas in A. So if we go to that boundary where we are going from a liquid to a gas, we'll trace down and find that boiling temperature, which will be 50 degrees. Okay, now let's try this next one right quick. It says if the temperature of a substance is held constant at -15 degrees Celsius, so here's that on your x-axis, what phase change would occur if you increased the pressure from 1 atmospheres to 30 atmospheres? So it's kind of this transition here, 1 atmosphere to 30 atmospheres. So when we start out at -15 and 1 atmosphere, we're in the gas zone, and then we'll end up in the solid zone. So transitioning from a gas to a solid is called deposition. Then finally, let's do just one more. This one is easier. It says the triple point of this substance occurs at what ordered pair? So the triple point, again, is where all 3 states of matter coexist in equilibrium, and that occurs at a temperature of -15 degrees Celsius and 6 atmospheres of pressure. All right, so there you go, and good luck as you practice.